Hello everyone, welcome back to the HFSS tutorial for EC475. Today we want to talk about high gain antenna and how to design a horn antenna as one of the most useful and practical antenna. So let's see and talk about the horn antenna. They use a horn antenna for uh, many applications, like using in feeding elements as feeding elements of the reflectors and lens, or uh, using the feeding element of a large radio astronomy and satellite tracking. Uh, as you know, one of the simplest and most widely used in a microwave antenna is the horn antenna, and the history backs to the during the period of the World War II. At that time, a number of articles have been written describing its radiation mechanism, optimization, or design methods and applications. As I said, the horn is widely used as a feed element, like for large radio astronomy, satellite tracking, and uh, communication dishes, and they use as a feed for reflectors and lens, and it's a common element of a phase array and serve as a universal standard antenna for use in a reference standard antenna for gain and pattern measurement for other high gain antenna and other antenna. If you uh, go to the antenna lab, antenna measurement lab, you can see many range of the reference and standard horn antenna, uh, from 400 megahertz to uh, terahertz actually, which has a high gain and high directivity to measure the pattern and the gain of another antenna. And as you can see uh, in the picture, they're using a different form, like E-plane, H-plane, pyramidal or conical shape. As you know, the horn is nothing more than a hollow pipe of a different cross section, which has a tapering onto a large opening and aperture. The type, direction, and this tapering, the amount of the taper or flare, can produce many shapes, and it extremely affect the overall performance of the elements and the antenna as a radiation. For example, as you can see in the A picture, E-plane, uh, the sectoral horn is in this picture. You can see the opening is flared in the direction of the E field, and they called E-plane opening, or for the B1 is the H-plane opening. That's the name for this antenna. And the aperture field, as you can see in the picture, the aperture field is tapered to the large opening, and this large opening can manage or construct the radiation, can radiate the electromagnetic field into the free space, and you can shape and manage the field through this tapering. And let's go to the HFSS and see how to design it. Horn antenna. Today we want to see and design a horn antenna in HFSS in the frequency of 5 GHz. As you remember from the last lecture, we uh, we designed an array of antenna, 4x1 array or 1x4 array of the patch antenna, which these 4 elements have the gain of to 12 dB. and we can see here the gain of this the antenna for the 5 GHz is also for the single element horn antenna is also equal to the 12 dB. So let's move on to the HFSS and see how to design antenna. So we insert the HFSS design and draw a box for the transmission line and feeding structure. We create a box. The position will be 0, 0, 0. X size will be 30 millimeter. Y size will be 50 millimeter, and Z size will be 25 millimeter. And then we create a box. We should select the face, the front face, and select the surface to create an object from this face. Okay, and then sweep along the vector, sweep a profile along the vector to create a 3D object. Okay, which vector? So just draw one vector in a x-axis, and let's say draft angle 15 degree and draft type extended. Okay, and here we can see the box. Sweep along your vector. Which vector? So 15, 0, 0, draft angle. Yes, it's gonna be 15. Yes, 15, 0, 0 along the x-axis. Draft angle is gonna be 15 and draft type is extended. You can see the whole antenna right now here. So we need to again select this face, go to the surface and uncover the faces, because we need to propagate and also uncover these faces. Okay, we can see inside the horn. Now Control A or select all the sheets, and go to the again to a sheet and the thickness of the sheet. It will be 1 millimeter in both. So again you can see a thickness of the horn antenna here, and we change the material of the box. The assign material, we assign a PEC to our box. So and we unite these two sections, the horn section, the tapering section, and the waveguide section, the feeding structure. Okay, and then we should again select the inside face, that face, assign excitation, waveport. Let's see, the number of modes gonna be 3. because we want to see that the first mode propagate inside the waveguide, not the second and the third mode will not be propagate, and just we wanted to make sure that the first mode propagate inside the waveguide and radiate inside the horn antenna and tapering section. And because we want to see the three mode of this waveboard and see which mode is propagate and see the result. So everything is okay. For a boundary, we're gonna use the PML perfect match layer. The perfect match layer is used to for a large structure like horn antenna, is a perfect match layer, and there is no back propagation or a scatter from the whole media. This is an open media, and by using the PML, because it's a match layer, there is no reflection outside the box. And in this, for using the open region, we don't use any boundary region, and just select the PML and our operating frequency, which is we're gonna design the horn antenna in a 5 GHz frequency. So if you see this PML, you can see they are not visible, and right now you can see the PML are in a box inside it. You can see the structure here, and it's another way to use a boundary condition which is perfectly matched to the other side open region. And there's this another technique to use a boundary condition and solve especially for a larger structure like horn. And right now this is PEC, and let's validate. Okay, we don't have the analysis setup. Let's go to the analysis setup, advance 5 GHz, maximum number of pass, let's say 10, 22, advance, yes, and sweep from, yes, that's gonna be okay. And we have a radiation, sphere for our setup, everything gonna be okay. And okay, for the for the excitation 7.4. So just we wanted to make sure that we solve the ports only at 5 GHz, because we need to see the modal analysis and see which mode is propagated inside the first mode, the second mode, or third mode, which mode is propagated inside the waveguide. So let's validate our results and analyze. Okay, save it. Okay, so let's go to the results. Okay, and solution data, and converge. So what's happening? This is something error. Frequency 2.5 gigahertz. Okay, let's leave the sweep. Okay, now let's see in a 5 gigahertz. The last time it's 2.5 gigahertz. I don't know why, because it's we set the analysis sweep. Okay, in a 5 gigahertz, you can see the lambda and the gamma and epsilon of the modal analysis, and for the second mode and the third mode you can see this is 0, and it says that it doesn't propagate the second mode and the third mode inside the waveguide and our feeding waveguide. So it works for 5 gigahertz and our first mode. And let's go back to the analysis setup and solve it in a frequency sweep around 2.5 to 7.5 gigahertz. And now we can validate our simulation. Let's go to the solution data, go to the convergence, and see where the number of the passes. Okay, it's converge. It's converge in a 4 pass, and let's see the results. So let's go to the far field and 3D polar and see the 3D gain of the antenna. Okay, as you can see, it's in a bore side of the aperture of the antenna in 5 equal to 0, which is the x-axis. This is the x-axis, 5 equal to 0, and you can see the opening of the antenna. Also, we can go to the 3D mode and see the radiation field here. As you can see, it's okay. It's assuming that the center of the phase of the antenna is in the 0, 0, 0, the position of 0, 0, 0, but it's okay. You can see the maximum pattern is maximum gain is in the bore side of the antenna, and we can now see the E-plane and H-plane pattern of the antenna in another result figure. Okay, E-plane is the plane which have a two axes, the E field and the propagation direction. So here the propagation direction is in x-axis and E field is the z-axis. So xz is E-plane and the xy is H-plane. So let's see the xy, which is theta is equal to 19. So the primary sweep will be in a phi, and let's see in a dB, and the theta is equal to 90 degree. Okay, here you can see the H-plane of this antenna, and if you add a mark here, you can see the gain is equal to 10.5 dB. As you remember from the last lecture, the gain of the 4-array microstrip antenna is equal to 12 dB. So this is a single element and this is a high gain antenna. And so also we can see another result. Let's go to the antenna report data table and let's see the antenna parameters. So we can we can transduce and show. Okay, you can see the peak directivity is 11.5, peak gain is 11.9, and radiation power radiated power, when the incident power is equal to 1 watt, the radiation power is larger than the efficiency is larger than 1, because we use the perfect electric conductive PEC. Okay, so if you use the copper, this radiation efficiency and radiated power will decrease. So also we can see the S parameter of the antenna. Okay, let's see the S parameter of the antenna. Okay, S11 dB. As you can see, it's a wide variety. The S parameter, the magnitude is if you wanted to radiate in a much more higher bandwidth, the horn antenna will be useful for ultra wideband antenna and useful for wide range of antenna, and that's why, because it's high gain and wideband antenna, they use as a reference antenna and a standard reference antenna for measuring another high gain and pattern antenna, as you can see, at the 5 gigahertz, and from, let's see the marker here, from about 3 gigahertz to, I don't know, about 3 to 10 gigahertz, this antenna works and radiates power, and at 5 gigahertz we can see it's a minus 25 dB, almost minus 26 dB has the S11, and all the powers radiate to the free space. Okay, in this lecture we saw how to design a horn antenna in HFSS, and we see the pattern of the high gain antenna, and we see how to see the E-plane and H-plane of the antenna, and radiation gain and power. Thank you.